Good morning, sir. This is Bhavya Jha from first year Computer Science and Engineering Department, and today I'm here to give a presentation on binary search traversals with examples. This is a part of the presentation CAA2 assignment for data structures with the subject code of 23 CAC01. So moving on to the question part. Now, what is definition of binary tree? A binary tree is a fundamental data structure in computer science, defined with the following characteristics. Hierarchical structure. A binary tree is a tree data structure where each node has at most two children, which are referred to as the left child and the right child. Now, what is a root node? It has a unique starting node called the root, from which all nodes branch out. The root of a binary tree is the topmost node without any parent. Leaf nodes. Nodes without any children are called leaf nodes. These are the terminal nodes of the path starting from the root. Now, understanding what is depth first search and breadth first search. So, depth first search. DFS technique. The very first point is path exploration. DFS explores as far along a branch as possible before backtracking. Stack utilization. It uses a stack either explicitly or through recursion to keep track of the next vertex to visit. Breadth first search. Level order traversal. BFS explores all neighbors at the present depth prior to moving on to nodes at the next depth level. Queue utilization. It uses a queue to manage the set of next elements to explore. BFS ensures that it explores nodes in order of the distance from the start node. Pre-order traversal. It is a DFS technique. So pre-order traversal is a method of visiting all the nodes in binary tree and is one of the three depth first search techniques, that is orderings: pre-order, in-order and post-order. Now here's how it works. First we visit the node, that is we start by visiting the root node. Then we traverse the left, that is recursively perform a pre-order traversal of the left subtree. Then we traverse to the right, that is recursively perform a pre-order traversal of the right subtree. Now in the next slide we'll be understanding how it works briefly. Now pre-order traversal. As we can see, a tree is given with its left subtree having B, D and E, and its right subtree having children C and F, and A being the root node. So according to pre-order traversal, we visit the root node A first, then we move to the left subtree of A, that is we visit B. Now move to the left subtree of B, that is we visit D, and D has no children, so backtrack to B. Then we move to the right subtree of B, that is we visit E. Now E has no children, so we backtrack to B again, then again back to A. Now we move to the right subtree of A, that is we visit C. Now we move to the right subtree of C, that is we visit F, and as we see, F has no children, so the traversal is complete. Now the pre-order traversal of this tree would be A, B, D, E, C and F. Now this method is often used when you need to explore roots before inspecting the leaves. So obviously this technique is pre-order traversal is nothing but root, then you go to left, then right. Now moving on to the next technique, which will be in-order traversal. Now as the name in suggests, which means that root is between left and right. So first we explore all the left subtree, then we visit the node, and then we go to the right subtree. So in-order traversal is another method used to visit all the nodes in a binary tree. It's a type of depth first search that follows a specific order, that is left subtree, node and then right subtree. Now this method is particularly common for binary search trees because it returns values in non-decreasing order. So steps for the in-order traversal. Now this is just a brief discussion that we'll do. We first traverse the left subtree, that is we begin with a recursive in-order traversal of the left subtree. Then we visit the node, that is after the left subtree has been visited, we process the current node typically by printing the node's value or adding it to a list, and then we go to the right subtree, that is we complete the traversal by recursion, performing an in-order traversal of the right subtree. Now these techniques can be implemented both recursively as well as iteratively, but the recursive versions are much more easier when compared to the iterative versions. So we definitely prefer to go with the recursive versions. So now here's a brief discussion with an example of a tree as we saw in the last pre-order traversal technique. So what we do is we start at the root node and move to the left subtree, that is we visit node B, then we continue to left subtree, we visit D, we see that it has no children, so we backtrack to B again. Then we process node B. Then we move to the right subtree of B and visit E. E has no children, then we return back to A. So process node A, then we move to the right subtree of A and visit node C. Now node C has no children, has no left child. So we process C and then we move to the right subtree of C and visit F. Now we see that F has no children. So finally we end our traversal because A is already processed. So the in order traversal of this tree would be D, B, E, A, C and F. Now this sequence reflects visiting the leftmost child first, then the parent and finally the rightmost child. Similarly, we have this post-order traversal technique, which is again a DFS technique. So we have this post-order traversal, which is a method of visiting all the nodes in a binary tree and is the last of the three depth-first search techniques, that is pre-order, in-order and post-order. So in post-order traversal, nodes are visited in the following sequence. We have the left subtree, right subtree, and then the node itself. So again, we move on to the steps part. So we traverse the left subtree, that is begin with the recursive post-order traversal of the left subtree. Then we traverse the right subtree. After completing the left subtree, we proceed with a recursive post-order traversal of the right subtree. Then we visit the node. After the left and right subtrees have been visited, we process the current node, typically by printing the node's value or adding it to a list. So here's the technique. We start at the root node and move to the left subtree. At node B, we proceed to its left subtree. We visit D, then we return to B. We move to the right subtree of B and visit E. E has no children, as we can see in the diagram given. So we return to B. After visiting both children of B, we process node B. Then we return to A and move to its right subtree. So visit node C, move to its right subtree. We visit F, it has no children, so we return to C. Then after visiting the child of C, we process node C. And after all the subtrees of A has been visited, we finally process node A as well. So the post-order traversal of this tree would be D, E, B, F, C, A. So this sequence ensures that both the children or all the descendants of a node are processed before the node itself. Now let's understand a BFS technique as well, which is nothing but the level order traversal. Now level order traversal is also known as breadth first search technique for trees. It visits all the nodes in a binary tree level by level, starting from the root. Now this method uses a queue to keep track of nodes to visit, ensuring that nodes are visited in the order they appear in the tree. Level order traversal is particularly useful for finding the shortest path and for checking the completeness of a tree, or for serialization and deserialization of a binary tree. So we initialize a queue. We start by placing the root node in a queue. We process the nodes and then we repeat, that is continue the process until the queue is empty. So we will not be discussing the implementation of this level order traversal because it is not a part of the syllabus. And so moving on to the next slide. We have the time and space complexity. So the in-order, pre-order and post-order, which are DFS variants, take time complexity of big O of n into big O of n for all the DFS techniques. Why? Because each node is visited once. Space complexity is big O of h into big O of h, where h is the height of the tree. And due to stack used for recursive calls or explicit stack usage, in the worst case, that is a skewed tree. A skewed tree is one which continuously travels in one particular direction and it does not go in the other direction. So at that time, it would become big O of n into big O of n. Now we have the level order traversal. Time complexity is same, big O of n into big O of n, because it's similar to DFS. Space complexity on the other hand is big O of w into big O of w, where w is the maximum width of the tree. So importance of traversal technique. The first one is data retrieval. Different traversal orders allow data to be retrieved from a binary tree in specific sequences, which can be crucial for certain applications. And expression evaluation. That is, trees are used to represent and evaluate expressions in compilers and calculators. So post-order traversal is particularly useful for evaluating postfix expressions, etc. So here are some more advantages. That is building and maintaining indexes, network broadcasting, resource management, and rendering scenes. Now this was the entire synopsis. What is binary tree, their important components, two major traversal technique, brief explanation, examples, time and space complexity, and finally we understood the importance of traversal techniques. So with this, I end my presentation. This is the presentation by Bhavya Jha from first year Computer Science and Engineering Department. Thank you.